Now let's start the second part of today's lecture. Now that we have mathematical notation for concrete syntax, or actually abstract syntax of this language, let's review how to write the operation semantics. The usual thing, the numbers n is evaluated to a number n. Previously, because the integer function returned int, this number n was n, but now that we have this value, new type for return value, num n is now num vn in the Scala implementation. In the Scala implementation of the interpretation, num is an expert, num v is a value. So in the Scala implementation, we have to distinguish between this expression and a value. In the operation semantics, again, this blue notation is for the template. The way we write the operation semantics of FAE is under the sigma. When we evaluate, when we interpret this expression E, it results in the value v, which is just the same as when we call this interrupt function with, what's the first argument? Expression. E, what's the second argument? Environment. Sigma, then it's going to be the result v. So these things are just the same. When we have an expression, we can describe its semantics as in Scala implementation of the interpreter, or we can describe that in operation semantics. How do we represent this case in the operation semantics? Under this given environment E and V, when we interpret this expression E, which happen to be this num n, the result is going to be num vn. Meaning that under this given environment sigma, when we evaluate an expression n, it evaluates to a number n. Here it's going to be num n, this is going to be num vn. Addition, just like as before, we interpret the first sub-expression, get the value, we evaluate the second sub-expression, get its value, and then add them. In the operation semantics, as before, there's nothing new here. Under a given environment, when we interpret E1 plus E2, what's the value? That's in order to know the value, we need to evaluate the first sub-expression and the second sub-expression under the same environment, sigma, and get their values. They should be both numbers, n1 and n2, and then we are going to add the values. So in this operation semantics, we made it clear that the result of evaluating E1 and E2 should be numbers. Again, in this language, the result is going to be value v, and v is either number or closure v. And this operation semantics makes it clear that for the addition, the values of two sub-expressions should be numbers. So when we ask you to write the operation semantics for a given expression, if you say v1 and v2 here and write this like v1 plus v2, it's wrong. You're going to get penalty if we write that. Why not? Because we know how to add n1 plus n2, but we don't know how to add v1 plus v2. Why not? Because this v1 or v2 could be closure v. Do you know how to add 3 plus lambda x dot 4 comma empty environment? Do you know this? I don't know. So it's an error. So in order to allow the addition of these two sub-expressions, their values should be numbers. Did we check that in this Scala implementation? Yeah, remember this interrupt and this interrupt, they're going to return value which are either num_v or cl_v, and this num_v add function that had to check, hey, you and you, both arguments, are you guys num_v? If not, it's an error. If you're a num_v, then you should be like num_v and 1, and you should be like num_v and 2. Then this one is going to get those two numbers, add them, and then put num_v back, like num_v and 1 plus and 2. Okay? Subtraction, just the same. We are not going to go into the details of subtraction because you should know this by now, right? How about identifier? Yeah, nothing new again. Under this given environment, when you have a name, you are supposed to check whether the name has a binding in this environment, meaning that because the environment is a mapping from names to values, whether the domain of this environment mapping includes this name X. If yes, then we are going to get the value bound to this name in the environment. If not, this rule does not say anything, meaning that there's no rule to apply, which is an error. How about function expression? Yeah, this is pretty new, but yeah, it's so obvious, right? You know how to do it. You don't know? Then let's look at this implementation. What did we say? We are interpreting this function expression, right? We are interpreting this expression, which happened to be this function expression. And then this function expression meaning it's an anonymous, unnamed function which has parameter x whose body is b. And what did we say? Interpreting this function expression results in closure v with this parameter name, body expression, and the environment. Then when we interpret this lambda x dot e function expression, lambda x dot e under this environment sigma, then what do we construct? We construct this closure v of parameter name x, body expression, and then sigma. So far so good? Yeah? Then how are we supposed to write down the evaluation of function call? Yeah, now you can smell that the next slide is going to be the most important slide for today because that's function call, right? So this language is called FAE, and later we are going to extend this language FAE with various features like mutation, continuation, types, and things like that. But most of the time, the baseline is FAE. 우리가 이 언어를 여러 가지 피처를 가지고 확장할 거예요. Exceptions, 변수, continuation, things like that. But when we extend this language with multiple features, the main idea is FAE, and always the most important thing is function call. Whatever you add. 어떤 피처를 더 추가하더라도 가장 중요한 건 보통 function call이에요. Let's see. Yeah, actually the Scala implementation was also slightly more complex for function call, right? Let's see one more time. When we interpret an expression, which is a function call of FNA, we first interpret the first sub-expression under the given environment. Then it should be closure V. Otherwise, it's an error. If it's a closure V, because we made it that way, it has three fields. Its parameter name, body expression, and the environment when this closure V was constructed. Then we interpret the argument expression under the same environment, get the value, and remember that the parameter name, this parameter name has the value. We extend the given the environment when this closure V was constructed, the environment when the function was being defined with this parameter's value information, and then evaluate the body expression. Is it clear? Yeah? You should be able to see the semantics so that you can write down this operation semantics rule. We will read through this rule in a minute, but before that, let me emphasize this. First in English and then Korean. When we have a new language feature, just like first-class functions and function expressions and function calls like that, we discuss its syntax and semantics. For the semantics, I often give you examples, code examples, and explain that in prose, meaning in English, and then implement the semantics in Scala, and then describe its semantics in operation semantics. Let me repeat this in Korean and get back to English to emphasize the main point. 우리가 새로운 언어의 새로운 피처를 배울 때마다 예를 들어 이름 없는 함수, 함수가 값인 first class functions, 함수 expression, 함수 call 뭐 이런 거 배울 때 처음에 언어를 확장하고 그 의미를 example 보고 많이 얘기하죠. 코드 example 막 보여주면서 설명하죠. 그리고 그거를 스칼라로 구현을 해요. 그 다음에 operation semantics를 어떻게 쓰는지 해요. That's the pattern. From the new concept, explain that in prose, mostly in English, and then show you some code examples, implement the semantics in Scala, and write down the operation semantics. That's the pattern. And you should be able to do that by yourself. In your midterm exam, we may ask you, or we may introduce new language construct or new language concept and explain that in prose. We may give you some code examples, and we may ask you to implement the semantics in Scala. We may ask you to write down the semantics in operation semantics. So all those patterns, all those sequence, you should be familiar with before the midterm exam. 중간고사 보기 전까지 그 패턴에 익숙해지셔야 돼요. 새로운 피처가 있을 때 걔가 뭔 소린가? 아, 그게 이런 코드 example이구나. 스칼라로는 인터프리터 구현을 이렇게 해야겠네. 그거는 수학적으로 오퍼레이션 세맨틱스를 이렇게 써야겠네. You should be able to do that sequence by yourself. That's why we are going through this sequence again. And now, when you know that function call is this, when you know the semantics of function call, which is evaluate the first sub-expression, get its closure V, evaluate its body under this environment, that's semantics, right? You should be able to explain that in prose, meaning in English. You should be able to implement that in Scala, meaning that if I give you just, the template and you should be able to fill in this part. 여기 비어있어도 이거 채울 수 있어야 돼요. And you should be able to write down this operation semantics by yourself based on your understanding of the semantics. So what are you supposed to do again? Let's see. When you know the semantics of function call, what you're supposed to do is, function call needs this E1 and E2. Function call in FAE requires two sub-expressions. And when you interpret this new expression, you need an environment that's given to evaluate this expression. Under this given environment, sigma, how are you supposed to evaluate E1, E2? Let's see. First, how are you supposed to E1, E2 under this environment? The first thing is to interpret the first sub-expression under the same environment. Interpret the first sub-expression under the same environment. Do you see the correspondence? You should be able to, right? You should be able to find the correspondence saying interp. Interp. The first sub-expression under the given environment, And what does it say? And that should be closure V with the parameter X, body B, and the environment FEMV. Evaluating this first sub-expression should be closure V. It cannot be number. It should be a closure V with parameter name X, body E, and environment sigma prime. This is sigma prime. You can write it like sigma 1 or sigma whatever, but that should not be sigma. As soon as you say sigma, that means that the given environment should be in this closure V. Really different thing, right? Yeah. And then what are you supposed to do next? Interpret the second sub-expression under the same environment. Interpret the second sub-expression under the same environment and get the value, and that value should be X's value. Okay, let's call it V2, and X's value should be that value, and we are going to add that information to the given environment. We are going to add that information to which environment? Not EMV, but FEMV. Not sigma, but sigma prime. Sigma prime. Under that environment, evaluate the body expression. That's going to be the value of this function call. Okay, under this new environment, evaluate body expression. Where is it? Here. Body expression E, and get the value. That value should be the value of the function call. Are you with me? Again, this is the most important slide for today. Function call. Function call is always the most important thing. So whenever we have a new feature, you should be able to see how that feature changes the semantics of function call, right? And again, for that, FAE is the bare minimum. FAE is the baseline. So you should be able to just say this out of thin air. When I just ask the question, you should be able to write it down. Like, E1, E2, under the given environment, we first evaluate we are gonna evaluate E1 and E2, both of them under the same given environment. That's the environment at function call site. And E1's value should be closure V, and closure V has parameter name, body expression, and the environment when this closure V was constructed. And that environment may not be the same with this call site environment. They may not be the same. They may be the same, but that's coincidence. They may not be the same in general. And when we evaluate this function body B, we should use this sigma prime. That's a static scope. If we use sigma, that's dynamic scope. On top of sigma prime, we need to put this information saying the parameter's value is going to be the value of the second sub-expression. And using that extended environment of this static scoping, get the value. That's going to be the value of function call. You should be able to say that. Okay. So before having the second break, meaning that before having the second quiz, let's see the main core calculus behind all this. I've been telling you about FAE. We are going to shrink the language. We've already seen that val is not really necessary when we have function expression and function call. Remember, we used to have FVAA, but we realized that V is not needed because we can simulate that by using function expressions and function call. And actually, it turns out that those fancy things like numbers, addition, and subtraction, they are not necessary either. Really? How come? Oh, we'll see that. And actually, all we need is love, right? But all we need is these three things, function-related things. It's identifier, function expression, and function call. Ooh, only three things. We call that LC for lambda calculus. LC for lambda calculus. Okay? And lambda calculus is Turing complete, meaning it's just powerful enough to do whatever you want to do. And it has only three language constructs: identifier, function call, and function expression. What about numbers? What are numbers? Yeah? So this one is going to be, again, only three language constructs, and using only three, you can write down any algorithm. Wow. Can you write a program in LC that produces the identity function? Oh yeah, for sure. This is what? This is LC, lambda calculus, because yeah, it's a function expression. It's an identity function. Okay, how about this? Can you write a program that produces 0 in LC? Can you write a program that produces 0 in lambda calculus? What is 0? I only know how to write functions, right? And Turing machine programmer will say, what's a function? I only know how to write 0 or 1. In Turing machine, everything is binary. So we need to encode 0 instead of agreeing to write 0 as this circle thingy. Yeah, that's the promise some people made some time ago, but I don't want to write that. I'd like to write this, and this is 0. Are you with me? You may not like this idea, but and this may sound crazy, but this is my 0. And this encoding is the start of church numeral, which is really famous. In church numerals, we can simulate many things in lambda calculus. I will say this is a function expression which takes a parameter, and the body is yet another function expression which takes another parameter and returns x. That's true. And you take two parameters and return the second one, that's false. It's encoding, right? I write this and call it true and false. 이렇게 쓰고 true라고 false라고 읽는다. 이렇게 쓰고 0이라고 한다, 1이라고 한다, 2라고 한다예요. Yeah, I write this and that's 0. This one is 1. This one is 2. Ooh, what the? Why? Why? Look at that. There's a pattern even. This is the number of the application of the first parameter. See, it's just encoding. You may think it's crazy, but actually, this is from 1930s. Oh, there's no picture. I'm gonna put pictures in your slides later. And in the 1930s, really famous people like Alan Turing and Alan's church, they found the same thing independently. 각자 따로 연구했는데 같은 거를 발견하셨어요. 아주 훌륭한 시대죠. Alan Turing defined Turing machine, Alan's church, and others defined the lambda calculus. In a computational system that can compute every Turing computable function is called Turing complete. If you don't get it, don't worry. You'd better take CS320 algorithm course and you're gonna learn that. 그러니까 뭔 소리인지 모르시면 알고리즘 코र्스를 들어보세요. That's not the main point for today's lecture. The main point is the lambda calculus is Turing complete, meaning that the lambda calculus, it has only 3 language constructs, but it's powerful enough. Wow, it's amazing. Encodings of high-level constructs in the lambda calculus are church encodings. Yeah? So you don't need to remember all those encodings and what. 지금 람다 캘큘러스 열심히 설명했는데 이거 다 외우지 않아도 돼요. This is just the background, awesome, beautiful mathematics behind operational semantics and functional programming. Okay, and more explanation is available in these documents. And exercise number 5 is available from Piazza. As usual, I recommend you to do exercise number 5 to be prepared for that difficult take-home open book exam. Okay, so far so good. We are gonna take the second break here and we will resume at 3:30 for your quiz number 2.